Next heading, cyclic structure. Cyclic structure of evidences for the cyclic structure. Evidences for the cyclic structure. Number one, despite having the aldehyde group, despite having the aldehyde group, glucose does not give 2,4-DNP test. NaHSO3 sodium bisulfite addition, NaHSO3 test and Schiff's reagent test. Despite having the aldehyde group. In the previous chapters, that is aldehyde of carboxylic acid, we learned these in the previous chapters, we learned the reactions of aldehyde group with 2,4-DNP NaHSO3 Schiff's reagents. But here, glucose does not give these tests. So what are the reasons for this? This is due to the cyclic structure. Number 2, pentaacetate of glucose. Pentaacetate of glucose does not give the reactions of even strong reagents, that is hydroxylamine and H2OH. Pentaacetate of glucose does not react with pentaacetate of glucose does not react with H2OH hydroxyl. I mean, it's a strong reagent. So despite having an aldehyde group, glucose does not give the test of aldehyde group, test of carbonyl group. Pentaacetate of glucose does not react with hydroxylamine. And glucose exists in two forms, alpha form and beta form. Glucose exists in two forms. Number 3, glucose exists in two forms, alpha form and beta form. And 36% of alpha form and 64% of beta form. Number 3, this is the open chain structure. CHOH on third carbon, OHH, fourth carbon, HOH, fifth carbon, HOH, sixth carbon is CH2OH. This is the open chain structure. But this amount of this open chain structure is very less, that is less than 0.5% in a sample that you take. It is an equilibrium with alpha form. What is alpha we are saying? That is C, OH, H, C. This is with the C5. This is C1, C2. That is H, OH, C, OH, H, C4, H, OH. See here on C1, this is an anomer. On C1, OH is on the right hand side. OH is on the right hand side. So this is alpha. This is a cyclic structure, Hayward structure. Alpha form, this is 36%. And beta form, that is also there in this equilibrium picture. That is C. What is the difference between alpha and beta? OH on the first carbon configuration. On first carbon is different. C1, C2, H, OH, C3, OH, H, C4, H, OH. C5 connection and CH2OH, sixth carbon. This is 64%. So these are the evidences for the absence of aldehyde group. Some reagents are reacting with glucose, for example, HCl and NH2OH. They are giving irreversible products, means this will be removed from the reaction mixture. An irreversible product is from cyanohydrin and oxygen. These give irreversible product, means that will not be decomposing to form this back. So here it is empty. So this will open, that will open, or we can say HCl and NH2OH are capable of opening the cyclic structure. But what I said, 2,4-DNP, NaHSO3 and Schiff's reagent, they also react with this. All the reactions are going to this open chain structure. They also react with this, but they give reversible product. Means that product decomposes back to give this open chain structure. That means open chain structure is always present in this equilibrium. Once it is present, these two don't have to open up. That means those reagents are not capable of opening up this cyclic structure. So these are the evidences for the cyclic structure of glucose. Number one, despite having an aldehyde group, glucose does not give the products for DNP, NaHSO3 and the Schiff's reagent. Pentacetate of glucose does not react with hydroxylamine. Pentacetate means, I showed you last day, pentacetate here, 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 here. Five ester group attached here. So there is no aldehyde group, pentacetate. Since this ester group is there, then there is no chance of formation of an aldehyde group. So pentacetate of glucose does not react with hydroxylamine to give oxygen. These are the evidence for the cyclic structure of glucose. Next, we are moving to protein. Next, biomolecule protein. Proteins are the polymers of alpha amino acids. Proteins are the polymers of alpha amino acids. Alpha amino acid. What is meant by an amino acid? Amino group should be there, acid group should be there. Acid group is this one and amino group is monoester. So the smallest one with one carbon, for example, COOH and H, then NH2. This is an amino acid. This is an amino acid. Is this carbon optically active? No, because it contains two similar groups, two hydrogens. There are 20 amino acids. One is this. This is called glycine. Glycine. The next amino acid, that means I'm replacing this H by one CH3. Then we call it as alanine. Alanine. This is an amino acid. This is an amino acid. An amino acid can be represented by a three-letter word like GL1 or ALA, or a single letter, one letter, that is G or A. Amino acid can be represented by a three-letter word or a single letter, simple. Alanine. Now, this is alanine, where I replace glycine, see H from glycine. Now, if I replace one H from here and attach a phenyl group here, then we call it as phenylalanine. 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 We show by PHE or P. Phenylalanine. So glycine, alanine, phenylalanine, valine, leucine, isoleucine, like that 20 amino acids are there. Amino acids, amino group is this is basic, this is acidic. There may be more number of acid groups, there may be more number of NH2 groups, there may be equal number of NH2 and COOH group. If there are more number of COOH group, then we call it as acidic. If more number of NH2 group, then we say basic amino acid. If both the number of NH2 and COH groups are equal, then we say neutral amino acid. So classification of amino acids. Classification of amino acids. There are different classifications. That is acidic amino acid, basic amino acid, and neutral amino acid. And the number of COOH groups are more than NH2 groups, then acidic. If number of NH2 groups are more than COOH, then basic. When equal number of COOH and NH2, then we say neutral. And another classification is there: essential amino acid and non-essential amino acid. Essential amino acid and non-essential amino acid. Non-essential amino acid. Essential amino acids. It is very much essential for our body. The body cannot synthesize such amino acids. So essential amino acids are those amino acids which are not synthesized by our body. Essential. Essential examples are valine, leucine, non-essential amino acids, that is those amino acids which are already present in our body, you don't have to take from outside through diet. Essential amino acids are to be taken from outside, that is through the diet. Non-essential amino acids are the amino acids which are already present in our body, which we don't have to take from outside through our diet. Non-essential, glycine, alanine. Example, glycine, alanine. So essential amino acids, essential valine, leucine, non-essential amino acid, glycine, alanine. So these are the classification of amino acids. Amino acids are connected. I told you proteins are made by alpha amino acid. Alpha amino acid means CCH2, COOH, NH2. This is an amino acid alpha. Alpha amino. This is the functional group. This is alpha carbon. So alpha amino acid means this NH2 should be on the next carbon of this COOH. This is alpha amino acid. So amino acid proteins are the polymers of alpha amino acids. So I'm going to write alpha amino acid and I'm making them join to make a long chain, that is polymer, a long chain. So this is glycine, and now I'm going to write alanine. One H is replaced by CSC, that is alanine. This is glycine. This is alanine. So what happens? H from here and H from here. One H from here will go as water molecule. So these two compounds got connected. These two compounds got connected to a bond, means C will be connected to NH. CONH. So this is CONH, CH, CH3, COOH, and here CH2, NH. Now this COH can be taken out as water by taking one H from the next molecules, H of NH2. So here another bond CONH, like that. Here, NH2H and COOH, OH, the next molecule can go as water molecule, and one molecule will be connected here also. Means a long chain polymer will be formed. We call it as a long chain. If it is two, we call it as dipeptide. Here only two. This is a dipeptide. This is called the peptide linkage. This is called peptide linkage. Peptide linkage. Peptide linkage. This is a dipeptide because two molecules, two alpha amino acids are joined dipeptide. If one more comes over that side, then tripeptide, tetrapeptide, etc. If more than 10, then we call it as polypeptide. This is dipeptide, then tripeptide. Till 10 we say oligopeptide. Oligopeptide means 2 to 10, 3 to 10, oligopeptide. Oligopeptide. Then above 10, that is polypeptide. Above polypeptide, 10 has the polypeptide. Then above 100, then protein. Above 100, then protein. So if there are, write down, a dipeptide, what is a dipeptide? Two amino acids are joined. Tripeptide, three amino acids are joined. Tetrapeptide, 2 to 10 है तो we say oligopeptide, O-L-I-G-O. 2 to 10 oligopeptide. If more than 10 polypeptide, if more than 100, then proteins. So dipeptide, tripeptide, tetrapeptide, these are coming under oligopeptides. More than 10, then polypeptides. More than 100, protein. Now, classification of protein. Classification of protein under two categories: globular protein and fibrous protein. Fibrous protein. Fibrous protein and globular protein. Globular protein. Fibrous protein. See, hair. This hair. This is a fibrous protein. Fibrous protein. Polypeptide chain, the polymer, the polypeptide chains run parallel. When polypeptide chain run parallel means this hair has got many strands. One hair can be considered as of many strands. These many strands are joined together through hydrogen bonds, and you see that one hair. This hair can be split. Those polypeptide chains can be separated. When these polypeptide chains run parallel and joined by hydrogen bonds, we get this fibrous protein. For example, like this. Polypeptide chain run parallel and they are joined by hydrogen bonds. Keratin in hair, myosin in muscles. They are the examples for fibrous protein. Keratin in hair, and myosin in muscles. Keratin in hair, wool, silk, myosin in muscles. They are the examples for fibrous protein. Now, globular protein. Example, albumin of egg. Albumin, insulin, these are these are globular protein. When polypeptide chains coil around to get a spherical shape, when polypeptide chains coil around and get spherical shape, then we call it as globular protein. Example, albumin of egg, hemoglobin. Globin is a globular protein. Hemoglobin, that is the oxygen carrier, that is a globular protein. These are soluble in water. Globular protein is soluble in water, but hair is not soluble in water. So fibrous proteins are insoluble in water, while globular proteins are soluble in water. The structure of protein, next heading is structure of protein. Structure of protein is learned in different steps, different stages. Primary structure, secondary structure, tertiary structure, and quaternary structure. Structure of protein. Structure of protein is learned at different stages. That is number one, primary structure. Primary structure, secondary structure, tertiary structure, and quaternary structure. This is primary structure. Secondary structure is again classified into two portions. That is alpha helix and beta pleated sheet structure. Beta pleated sheet structure. And tertiary structure, quaternary structure. Quaternary structure. Primary structure, the specific sequence of amino acid is called primary structure. I told you these amino acids are joined by the peptide linkage to form that polypeptide chain. The specific sequence of amino acid like glycine, alanine, valine, leucine, glycine, alanine, valine, leucine, glycine, alanine, valine, leucine. Like that, the specific structures. Glycine, alanine, valine, leucine, 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 like that. I'll write that glycine, alanine, valine, leucine, glycine, alanine, valine, leucine, like that. A specific sequence of amino acids is the primary structure. Now, secondary structure, this polypeptide chain move around just like a screw when the polypeptide chains coil around. So it will be like this. And what happens? From here, see double bond O of one peptide linkage, then NH, between them hydrogen groups. So here, C double bond O and NH, between them hydrogen groups. Between them, C double bond O of one peptide linkage joins through hydrogen bonding with NH of the other peptide linkage. They are held together by hydrogen groups. So alpha helix structure, regular folding of the backbone of this polypeptide chains results into then C double bond O that will be making hydrogen bonds with H of NH of the next polypeptide, other polypeptide linkage. So due to this hydrogen bonding, means they fold, regular folding is there and it is an alpha helix structure. Alpha helix, you look at a screw, it will be going like this, it will be going like this. So just like a screw, it will be folding. Regular folding will give you alpha helix structure. Now, beta-plated sheet structure. These polypeptide chains are pulled to maximum extension. Polypeptide chains are pulled to maximum extension and laid side by side. Laid side by side so that hydrogen bonding. One will be making, that is CO of one will make hydrogen bond with NH, H of NH of the other. So C double bond O of one peptide linkage makes hydrogen bond with H of NH of the next other next layer. So polypeptide chains are they are pulled to maximum extension. Polypeptide chains are stretched to maximum extension and laid side by side, and CO of one layer will be making hydrogen bonds with NH of the next. So they are tightly packed. This is just like the pleats of drapery. These are the drapery, curtain pleats of a drapery. So we call it as beta-pleated sheet structure. Polypeptide chains are stretched to maximum extension and are laid side by side, which are held together by hydrogen bonds. So it resembles the pleated folds of a drapery. Pleated folds of a drapery. You know the curtain pleats, drapery pleats, and these pleats are joined by hydrogen bonds. So polypeptide chains are stretched to maximum extension and they are laid side by side so that CO of one plate will be making hydrogen bond with NH of the next plate. So it looks like a pleats of drapery. It looks like a pleated folds of a drapery. Now, tertiary structure. Further folding of secondary structure will be further folding of secondary structure will give tertiary structure. Here also hydrogen bonds will be there between CO and NH. There may be van der Waals forces, there may be electrostatic forces, all types of forces you can think of. All these forces are present in this tertiary structure. These chains are held together by hydrogen bonds, disulfide linkages, van der Waals forces, electrostatic forces. Now, quaternary structure. So here further folding of the secondary structure will give you tertiary structure. Now, for quaternary structure will be having subunit. So one is like this, and one will be going like this. That is protein structure composed of two or more polypeptide chains. See, one polypeptide chain, another polypeptide chain. Polypeptide chains is the quaternary structure. Protein structure composed of two or more polypeptide chains. That is called quaternary structure. So they have subunit. Each polypeptide chain is called subunit. Special arrangement of these subunits with respect to each other is known as the quaternary structure. Special arrangements of these subunits are called quaternary structure. So protein structures are learned at 4 stages: primary structure, secondary, tertiary, and quaternary.